Cubic zinc sulfide structure. Using lambda and rho from table 7 and the Madelung constants given in the text, calculate the cohesive energy of potassium chloride in the cubic zinc sulfide structure. Compare with the value calculated for potassium chloride in the sodium chloride structure. Okay, so table 7. Here's the table 7, properties of alkali halide crystals with the sodium chloride structure. Here is potassium chloride. We know nearest neighbor separation 3.147 angstroms. We know the repulsive energy parameter Z lambda 2.05 in 10 to minus 8 ergs. Repulsive range parameter rho 0.326 angstroms. All right. So for KCl, we have rho is equal to 0.326 angstroms, Z lambda 2.05, 10 to minus 8 ergs. In the sodium chloride structure, here is the sodium chloride structure. If we concentrate on this atom in the middle, we can count the number of nearest neighbors 1, 2, 3, 4, 5, and 6. So we have 6 nearest neighbors. Coordination number Z is equal to 6. It's the coordination number. And what is the R0 value? R0 value is 3.147 angstroms. So that is 3.147 angstroms. So we can calculate lambda because we know Z lambda. So lambda is going to be 2.05 10 to minus 8 ergs divided by the coordination number 6. So we obtain approximately 0.34 times 10 to minus 8 ergs. All right. What's the Madelung constant for sodium chloride? Sodium chloride Madelung constant is given in the text of Kittel 1.747565. So it is approximately 1.748. 1.748. Cohesive energy equations. These are the equations we worked with before. The cohesive energy evaluated at the equilibrium separation is minus alpha capital NQ square over R0. That's the Madelung energy, 1 minus rho over R0. For the potential energy as a function of R, capital N, Z lambda e to the minus R over rho minus alpha Q square over R. And we know that from del U del R evaluated R0 equals to 0, we obtained this equation, R0 square e to the minus R0 over rho is rho alpha Q squared over Z lambda. Since we have derived this equation before, we're just using this result for this calculation. All right, so that's obtained by taking the derivative of potential energy at R as a function of the derivative with respect to R evaluated at R0, set it equal to 0, we obtain this relationship. And then we substitute this result into U of R0 and we obtain this cohesive energy formula. Okay, so potassium chloride in the sodium chloride structure, we're going to use SI equation, so we need K, Coulomb's constant, 1 over 4 pi epsilon 0, which is 9 times 10 to 9 Newton meters square over Coulomb square. So the cohesive energy, U of R0, is going to be equal to, now we need minus alpha NQ square. So we have minus alpha n q squared, but instead of that we're going to use minus alpha k n q squared, so we will have 1.748 k Coulomb's constant, capital N q squared, divided by, let's see, we need R0, 3.147 angstroms, so that is 3.147 times 10 to minus 10, and then we have 1 minus rho over R0. So we're going to have rho 0.326 divided by R0, 3.147. So rho was 0.326 angstroms, R0 is 3.147 angstroms. So we substitute the numbers here. We obtain the cohesive energy U of R0 divided by K and Q squared to be minus 0.498 times 10 to 10, 1 over meters. This result is for the sodium chloride structure. All right, so this is for sodium chloride. Structure. And how did I get this 1 over meters? Well, Coulomb's constant K, capital N, Q squared has a unit. Coulomb's constant is Newton meter square over Coulomb square. Kq square over r square is the Coulomb force in Newton, so it is Newton meter square over Coulomb square multiplied by Coulomb square. Capital N is the number of molecules here. So we have Newton meter square, and the potential energy is in joules, so joules divided by Newton meter square is basically, joules is Newton meters as in work, F times delta X, divided by Newton meter square, so this gives us a unit 1 over meters. All right, so that's basically the unit of this quantity, U of R0 divided by K capital N Q squared. Notice that I don't have to convert these to meters here because they're both in angstroms. It's just the ratio. Now, if I work with the cubic zinc sulfide structure, this is basically the diamond structure with different types of atoms in the bases. So if you pick this atom here, we have 1, 2, 3, 4 nearest neighbors. So the coordination number is 4 in zinc blende structure, zinc sulfide structure. What is the Madelung constant? It is given in the text as 1.6381. Okay, so we're going to use alpha is equal to 1.6381. Rho, we will use the same value, 0.326 angstroms. And R0 square e to the minus R0 over rho is rho alpha q square over z lambda. And let's say that x is equal to R0 divided by rho. Now, 6 lambda is equal to 2.05 10 to minus 8 ergs, remember. That's the value we used for Z lambda here. Now I have 4 nearest neighbors, so the value I need to use is for 4 lambda, which becomes 1.37 times 10 to minus 8 ergs. All right. So with that, we have our 0 square divided by rho square e to the minus r0 over rho is equal to, so if I divide this by rho square, I will have alpha q square z divided by z lambda rho. So I have taken this equation and divided it by rho square, multiplied by 1 over 4 pi epsilon 0 to convert to SI units. This is equal to, let's plug in the numbers here, alpha value 1.6381, Q 1.610 to minus 19 coulombs squared, the Coulomb constant 9 times 10 to 9, divided by Z lambda value 1.37 10 to minus 8 ergs converted to joules. We have a 10 to minus 7, and then we have the rho value 0.326 times 10 to minus 10 meters. So this gives us 8.45 times 10 to minus 3. So r0 square over rho square e to the minus r0 over rho. So that's basically x square e to the minus x is equal to this value. So we can find what x is by trial and error. By trial and error, we find x, which is r0 over rho, to be approximately equal to 9.2. So since rho is 0.326 angstroms, this implies that r0 value is approximately 3 angstroms for this structure. Okay, now we can plug this in to cohesive energy formula. U of r0 is equal to minus, let's remember what we had there, minus alpha and q square over r0. So this is going to be minus 1.6381. Instead of nq square, we have k nq square, Coulomb's constant, divided by r0, which is 3 times 10 to minus 10. Then we have 1 minus rho over r0. Now r0 over rho is 9.2, so it is 9.2 to the power minus 1. And this gives us the cohesive energy U of R0 divided by K and Q square value to be minus 0.487 times 10 to 10 in 1 over meters. So this is the answer for zinc sulfide, zinc blende structure, zinc sulfide structure. So if we compare the cohesive energies, the cohesive energy for sodium chloride is minus 0.498, this is minus 0.487, is less than the cohesive energy for zinc sulfide. And remember, these values are compared to K and Q squared. So minus 0.498 10 to 10 is less than minus 0.487 10 to 10 in 1/meters. So what is the conclusion? Since the absolute value of the cohesive energy for sodium chloride is higher, it's more negative, we find that sodium chloride structure is more stable by comparing these two values. All right, so in this problem, we're talking about the zinc sulfide structure. We use lambda and rho values and from table 7 and Madelung constants from the text to calculate cohesive energy of potassium chloride in two candidate structures, zinc sulfide and sodium chloride structure. From table 7, we read R0, Z lambda value and rho in the sodium chloride structure. And in the sodium chloride structure, we note that the coordination number is 6 and the Madelung constant is given in the text 1.747565 or approximately 1.748. And we have these CGS equations. The cohesive energy is minus alpha capital NQ square over R0, 1 minus rho over R0, where capital N is the number of molecules and Z is our coordination number. Lambda and rho are basically the two fit parameters here. They're called, the rho is the repulsive range parameter and lambda is the repulsive energy parameter divided by the number of nearest neighbors. So these equations are obtained by basically setting this derivative of u of r with respect to r equal to 0 at the equilibrium separation and finding this relation and substituting it for r0 square e to the minus r0 over rho, this expression, we obtain this Madelung energy plus the repulsive term. So this is our repulsive term due to Pauli exclusion, and this is our attractive term due to Coulomb interaction. Okay, so we can find lambda value from Z lambda, noting that Z is equal to 6. Alpha is given, so we substitute these numbers into the cohesive energy. We find minus 0.498 10 to 10 in 1/meters. Instead of capital NQ square, we use K, Coulomb constant, times capital NQ square to convert to SI units. We have to do the same calculation in the zinc sulfide structure, cubic zinc sulfide structure or zinc blend structure. We know the alpha value, it is given in the text. We know the rho value. Rho value is basically the repulsive range parameter, the same parameter we use in the sodium chloride structure. What we don't know is the nearest neighbor distance, R0, and we can find that by noting this equation, and for q square we have to use kq square, and this gives us an equation x squared e to the minus x is a number. By trial and error we can find x to be 9.2. Since rho is known, R0 is 3 angstroms, and we can substitute that into the cohesive energy to find that we now have a lower absolute value of the cohesive energy, 0.487 times 10 to 10 per K and Q square. Since the cohesive energy absolute value is larger for sodium chloride, or it's more negative, we find that sodium chloride structure is more stable.